Okay, so last section we're going to look at this week is 6.4, and this will finish off the graphing and all the different trig functions look like. So we're going to use what we already know about sine and cosine to figure out what tangent would look like. So the way we're going to do it is we're going to rewrite tangent in terms of sine and cosine, and we just did this in the homework. Can someone remind me again how I can rewrite tangent as a fraction of two other trig functions? Yeah.
Sine of x over cosine of x.
Yeah, sine of x over cosine of x. All right, so now let's look at a couple questions. I want to know, first of all, when the graph of tangent would cross the x-axis. When would tangent be equal to 0? So looking at this fraction, can anybody tell me what would have to equal 0 in that fraction for tangent to come out to 0? Okay? When sine is 0. And we should know that. Okay? If you look at the graph of sine, sine crosses infinitely many times, but if I just focus on the first cycle, sine is 0 at 0. It's 0 halfway through. What's halfway through the cycle? Leo? Pi. And 2 pi is a repeat of 0. So basically sine is 0 at every multiple of pi. 2 pi, 3 pi, 4 pi, 5 pi, forever. All right? So that's where tangent is going to equal 0. But now, instead of looking at what happens when you have a 0 on the top, I want to look at what happens if you have a 0 on the bottom. Well, cosine definitely crosses the x-axis. So cosine can definitely equal 0. So what happens if you divide by 0? You don't get 0. You get something different in your graph that we haven't had before in a trig function. Sometimes you can get a whole if you have a common factor in the top and the bottom. We will not. So in this case, it won't be a whole.
Asymptote.
It's going to be an asymptote. So you're going to get a vertical asymptote everywhere that cosine is 0. So if we look at our graph of cosine, cosine starts at the top, comes down, keeps going. What's the first value that gives me, what's the first x value for cosine that gives me a y value of 0? Yeah?
Pi over 2.
So we have pi over 2. The next one is 3 pi over 2. The next one after that would be 5 pi over 2, 7 pi over 2, 9 pi over 2. So all those numbers I just named are the vertical asymptotes for tangent. Okay. And later on, so pi over 2 and 3 pi over 2 are the first two. I'm just going to jump ahead and show you a chart. Where is it? So pi over 2, that's one of the first asymptotes for tangent. So eventually this chart will kind of help us to keep track of where all the asymptotes are for the trig functions, and then where are the new asymptotes if we shift left, right, up, and down. Okay, but we have to talk about how to explain what these x1 and x2 things are. All right. Okay, so let's see if we can make a sketch of tangent. So what I'm going to do first is I'm going to draw some asymptotes. Okay. I'll put some at pi over 2, 3 pi over 2, and so on. Okay. I'm not going to sketch a bunch of them because I just want to focus on one section. All right, so put vertical asymptote at pi over 2. I can put one at 3 pi over 2. Okay, if I want, I can put one at negative pi over 2. They're equally spaced. Okay, the asymptotes occur regularly. Inside of the asymptotes is basically going to be one cycle, one period, one section of tangent. Okay? So if I sketch what's in between all of those asymptotes right there, I'm going to be sketching 2 cycles. All right, so let's put in tangent. And now I'm going to check a value very close to the asymptotes. Actually, there's one other thing I can mark. I already know the zeros. Pi is a 0, 2 pi is a 0, 3 pi is a 0, all multiples of pi. So pi is a 0, 0 is a 0, 2 pi would be a 0, and so on. So the graph is going to go right through that point. Now, let's go with the first 2 dotted lines. I'm going to pick a number just a little smaller than pi over 2 and a little bigger than negative pi over 2. Okay, and see what happens. So let's take negative pi over 2. And I want to go just a little bit bigger. So I'll just put plus 0.01. Okay, when I do that, I get a y value of negative 100. So it's way down. Okay. Now I'm going to check a value very close to pi over 2, but a little bit smaller. So I'll take pi over 2, and let's just go a little smaller, minus 0.01, positive 100, okay, basically. So just before pi over 2, you're way up there. So the graph has to go through all 3 of those red dots, and it's going to have a kind of a curve to it. Okay, so it's going to stay very close, start to get further away, and then get very close on the other side. So what you're looking at right there, that's 1 cycle of tangent. Okay, if I wanted the next cycle, I would just make a copy of that, put it right there. Now you're looking at 2 cycles of tangent. So let me make it a little bigger so you can kind of see. So what do you think the period is of tangent? How often is tangent repeating? Yeah. Well, that's how many times it's going to repeat, but what's the frequency of those repetitions? Focus on one point on the graph, and then look where that same point occurs again later on. Yeah?
Every 2 pi over 2.
Every 2 pi over 2, which would be?
Just pi.
Just pi. So if you focus on any point, like let's say we're the x-intercept occurs again pi units later, not 2 pi units later. So that's a big difference with tangent. The period is pi, not 2 pi. Now, if I asked you how many asymptotes are in one period, what would you say there? How many asymptotes are in one period of tangent? Yeah? Well, an asymptote can't be in both. All right? So if I say that these 2 asymptotes are in the same period, well, then the problem is, if you look at the next cycle, well, this asymptote doesn't belong to it, because we already said it belongs to the one before it. So now there's only 1 in the next cycle. So really, there's only 1 asymptote per period. Okay? However you want to think of it, you can say the asymptote on the left belongs to the period that follows it. So you could say, like, this asymptote, if I try to sketch it very carefully, and it goes up to right there. So that asymptote belongs to the period after it. The next asymptote, the period after it. Okay? So one asymptote per period. Okay, questions on the sketch of tangent? And if you graph it, then you can see the same thing that we just drew. Okay. Looks like the graph on the screen has a little bit more of a curve than mine has, but that's a basic idea. All right, I'm not going to go through all the same steps here, but you could go through all the reasoning. Cotangent is going to cross the x-axis when the numerator is 0. You're going to have vertical asymptotes when the denominator is 0. What's the difference between the fraction I have here and the fraction I had on the other page? Yep.
Cosine is on top, and on the other one it was sine.
Yeah, the cosine and the sine have switched places. So what that's going to cause is all the vertical asymptotes for tangent are going to become zeros in cotangent. They're going to switch. All the places where tangent crosses the x-axis, those are all going to become vertical asymptotes. So for cotangent, you're going to have a vertical asymptote at 0, pi, 2 pi, and so on. So let's take a look at that one. So I already drew them in. There's your vertical asymptotes at 0, pi, 2 pi. And notice the graph of cotangent has an x-intercept of pi over 2. If you go back to tangent, pi over 2 was an asymptote. So all the asymptotes and zeros switch places. And the direction of the curve switches. So instead of having a positive slope throughout the curve, cotangent has a negative slope. It's not a constant slope, it's a changing slope, but it's negative throughout the whole period. Okay, and the same idea here, however you want to keep it straight, but I would say the asymptote to the left belongs to the period that follows it. With the 0.1 asymptote per period. And what does it look like the period of cotangent would be? How often does that one repeat? Leo?
Once every pi.
Once every pi. Just pick a feature of the graph and focus on where it occurs again. Look at a vertical asymptote. You have one at 0, you have one again at pi. What's the distance between 0 and pi? Pi. So tangent and cotangent are actually the only two trig functions that have a different period than everything else. Okay, 2 pi is kind of the normal period. These two graphs are different. All right, so we just said that period of tangent and cotangent is pi. So what that means is if you took the tangent function, and Leo, can you give me a number?
5.
5. If I took the tangent of 5 and type that in correctly, tangent of 5, okay, I get that. Now, if I go one period later, tangent of 5 plus, and I'm going to move along the x-axis one cycle, what do you think I'm going to get when I hit enter? Yeah?
Same thing.
I'm going to get the same thing. Because that's exactly the same value one cycle later. You're at the same spot on the y-axis. Right? I could also do tangent of 5 plus, I could go 23 cycles later. It doesn't matter. As long as I go integer multiples of pi, I get the same thing. So I showed you an example with 5. Now I'm just showing you in general. Take any value and add multiples of pi to it. And when you evaluate the trig function, it's exactly the same. Okay? Same thing with cotangent. But you have to add a multiple of pi, an integer multiple. You can't add 1.6 pi. You're going to go a whole cycle or you don't go a whole cycle. You can't go halfway between. Any questions on that idea? Same idea applies in degrees. If you wanted to do it, it would be x plus 180n. And the reason that's kind of important is because when I ask you to describe all the asymptotes for tangent, you can't write every one of them. There's infinitely many. But there is a way to describe them by putting plus the period times n. Okay? So it's going to use that idea. or n times the period, same thing. So what this is saying is that all transformations work exactly the same as they always have. So if you know the transformations for sine and cosine, you don't really need to write anything down. So adding inside is your phase shift, multiplying inside, period change. Multiplying outside is an amplitude change. Adding or subtracting outside, vertical shift. Be careful with all the stuff that's inside. It's all the opposite of what you would expect. So any questions on the transformations? I guess if you wanted to write anything down, you could write that, and that summarizes everything. So you can replace tangent with sine, cosine, secant, cosecant, anything you want. And again, I've used the letters that indicate the order to do the transformations. There's no change in the precedence of the operations. Okay, that stays the same. Right, so what we've already done, you've already seen the most sketching we're really going to do by hand. Okay? Pretty much everything else we do is going to be on the calculator for tangent and cotangent, or just arithmetic. Okay? We're not going to do a lot of sketching by hand. Okay, so to find the period of tangent or cotangent, you do not use 2 pi over b. It's pi over b. Sine, cosine, secant, cosecant all use 2 pi over b. Tangent and cotangent are the only ones that don't. So, what I'm going to start to show you now is how do you find the asymptotes for a trig function. All the ones we studied today have asymptotes. Okay. Well, to find the asymptotes, you really have to know where the original ones are. Okay. If you don't know where the original asymptotes for tangent are, you're not going to be able to find the asymptotes in this one either. Because you're changing the period. So you're changing the frequency of how often they occur. Okay, so it's all based on where they were originally. So the way you do it is first find all the asymptotes in one period of the original. You don't need to find asymptotes outside of one period, because if you find everything in one period, that describes the function. Because outside of that, it's just going to repeat the same behavior. If you don't remember where the asymptotes are, that's why I'm going to give you a table in a little bit. But even if you don't have the table in your notes, as long as you have a calculator, you could make a sketch of tangent. You could look at it and find the asymptotes. Okay? We know that they're always going to occur at like 0, pi over 2, or pi. So just go to your table and try some values. 0 an asymptote? Nope. Is pi over 2 an asymptote? Yep. There you go. So pi over 2 is one of the first asymptotes for tangent. Okay, so find all the asymptotes in one period. And then you're going to set each asymptote, which for tangent and cotangent, it's only 1 per period. But you set each asymptote equal to the argument. Okay, that's the argument. And solve. And what that's going to tell you is where all the asymptotes in the first cycle move to. Because that's all we're dealing with. One period. Then if you want to describe where all the asymptotes move to, well, you take what you just solved for in step 2, and you just put plus the period times n. Okay, so you find where the asymptotes move to originally in the first cycle, and then put that they are going to repeat every period. That's this part at the end. And that idea not only works for asymptotes, but you can use it for finding solutions. If I ask you, here's a trig function, tell me every solution. Well, find all the solutions in one period, and then just put plus period times n, because they're going to repeat over and over. Okay. Any questions on that idea? All right, so let's see if we can find the period of this. And then I want to set it up on the calculator so I can see 3 complete cycles. Okay, what's for tangent and cotangent? Can someone remind me, what's my formula to find the period? Rebecca? Pi over b. And what's b in this case? 2. So the period of this is pi over 2. So now if I want to show 3 cycles on my screen, how wide, not tall, because we know the graph goes up and down forever. So for these kind of graphs, just set your y max and min -10 to 10. That's good enough. But how wide does my window have to be to show 3 cycles? Yep.
3 pi over 2.
3 pi over 2, however you want to do it. Right? Like if I said to you, I want you to put a window on the screen that's 3 units wide, you could do 0 to 3. You could do 10 to 13. You could do -2 to 1. All of those are 3 units wide. Same idea here. Depending on how you do it, you might cut a period off in the middle. Okay? If we can show complete periods, that's always nice. But let's try 0 to 3 pi over 2. And let's see what happens. So when I graph that, I'm going to get 3 periods, but I did cut one off kind of halfway through. So you get 2 in the middle, a half on the left, a half on the right. Technically, that's okay. But if I wanted to fix that, what values in my window would I have to adjust? Yeah? I'd have to adjust the x, min, and max. I would have to adjust it by, let's see. So a whole period is pi. So if I shifted each of the x values by pi, you would see exactly the same picture. If I shifted it by, it's either half pi or a quarter pi. Let's let me try a quarter of the period. Let's do a quarter shift. So I'm going to do plus, let's see, the period is, well, the period's pi over 2, so you know what, let's do a half shift. I think if you shift that by half a period, then you're going to bump this section to the left edge of the screen, and that will come out on the other side. Okay, so half of the period is pi over 4. So let's do plus pi over 4. So bump the x min to the right, and the x max. Plus pi over 4. Perfect. So now we're going to be looking at 3 cycles that are connected, not half cut off. Any question on how we did that? So sometimes you want to do that. You want to see a graph that it just looks nice, so you don't have half of it on the left edge of the screen and half of it on the right edge. Okay? All right, so here's 2 graphs, and I want to identify which one of those graphs is 2 tangent x and which one is 5 tangent x. As long as you know what the 2 and the 5 are doing, you should be able to visualize what the effect would be. What are the 2 and the 5 doing? What kind of transformation? Yeah, Gracie. No, because they're outside the argument. So it's not a horizontal stretch. I like the idea of stretch though. So that kind of tells you which one it is. Yeah, it's an amplitude change or a vertical stretch. So one of these is stretched more than the other. Anyone think they can tell me which one the one on the left would be? 2 tangent x or 5 tangent x? Yeah, Sam?
5 tangents.
Yeah, pretend like this was like a piece of metal wire. If you grabbed the ends of it and you started to stretch it, that curve in the middle would start to straighten out. It'll never be completely straight. Eventually, if you stretch it enough, it'll kind of look like it's lines. But that's just because you're zoomed in. If you zoom out, then it'll look curved again. All right. So the one on the left is 5 tangent x. The one on the right is 2 tangent x. To answer a question like that, it's very important that I show each graph in the same type of window. Because if I change the scale from one window to the other, I can totally change how the graphs look, and that's not an accurate comparison. So the window on the left and the window on the right are exactly the same mins and maxes. Okay. Any questions on that one? All right. So let's look at the last 2 graphs, which are secant and cosecant. All right. Can someone remind me, how do we type secant into the calculator? Because we don't have a button for it. Sam?
It's like 1 over sine.
It is 1 over something,
Cosine.
but this one is cosine. And cosecant is 1 over sine. Dylan, do sine and cosine ever cross the x-axis?
Yeah.
What's the y value when it crosses the x-axis?
0.
0. So if sine and cosine can equal 0, what does that mean is going to happen here?
They're going to be asymptotes.
We're going to get vertical asymptotes. In secant, you're going to get a vertical asymptote everywhere cosine is 0. So that would be like pi over 2, 3 pi over 2. Cosecant, you're going to get asymptotes everywhere sine is 0. So that'd be like 0, pi, 2 pi, and so on. Okay, so let's just look at that first. Secant, there's no asymptote at 0. Cosecant, there is, which should make sense. And now from there, we're looking at each graph here, you're really looking at a little more than 3 cycles. A cycle for secant and cosecant is 1 U shape, 1 N shape. So if I draw this very carefully, actually, you know what? Let's do it like this. Let's start here. Okay, I'm trying to stay to the left of that asymptote, and I'm going to put a box around 1 period. And now here I'm also trying to stay just to the left of the asymptote. Okay, so what's inside that red box is 1 period. So how many asymptotes are there per period for a secant or a cosecant graph? Okay.
2.
Yep, there's 2. 2 asymptotes per period. That third asymptote, you don't want to say that it's part of that red box because then the next cycle would be short an asymptote. Okay? So 2 asymptotes per period. Also, what's different about these graphs than any of the other 4 we've studied so far? These graphs don't do something that every other graph did. Yep.
Cross the x-axis.
They never cross the x-axis. And the reason why should be pretty obvious looking at the function. For a fraction to be 0, or for cosecant to equal 0, that fraction would have to be 0. What's the only way to make a fraction 0?
If the top is 0.
If the top is 0. Well, the top is never 0. So if the top is never 0, you're never going to cross the x-axis. So what ends up happening here is you have a gap in the range. These kind of functions, they go up forever, they go down forever, but they don't hit everything in the middle. To figure out what they don't hit, well, normally they don't hit -1 to 1. Okay. To figure out what that would be if you transform it, let's say you did an amplitude change and you doubled everything. Well, I'll show you what that would look like. Let's try in parentheses 1 divided by 2 sine x. Okay, you might think, oh, well, maybe it's just going to skip -2 to 2. Nope. Now it actually skips -1/2 to 1/2. Okay? And if you weren't sure what that was, you could do second calc maximum and figure out. Doesn't really matter which one you do. You can do any of them. Figure out the highest that it goes. But if you do that, you'll see that it is -0.5 and 0.5. Okay. If you did something like, let's do 0.5 sine x, now you're going to be skipping -2 to 2. Okay. You have a bigger gap in the middle. All right. Any questions on those graphs? Okay, so can anybody tell me, I mean, I already kind of said it earlier, but what does it look like the period is for secant and cosecant? And remember, this asymptote is not a repeat of that one. Those are different. Okay, I'll circle the ones that are repeats. Okay, the 2 that I circled are repeats. Okay? 2 pi. Yep. The first asymptote reoccurs every 2 pi, and the second asymptote reoccurs every 2 pi. So technically, you could say there's an asymptote every pi. Actually, I mean, there's asymptotes every pi units. But they're different. Okay, 2 different asymptotes. All right, so period, same formula as you use for sine and cosine. Okay, so this table kind of summarizes everything we've talked about with asymptotes. The column on the left are all the original asymptotes. For tangent, cotangent, secant, cosecant. They're all the asymptotes in the first positive cycle. The column on the right tells you how you get the new asymptotes. This x1 and x2, okay, all these numbers that I have written here, those are all calculated using step 2 from that slide. Set the original asymptotes equal to the argument and solve. Okay, so those are all step 2 from from earlier slide. So take the original value, set it equal to the argument, solve it, boom, there's your x1 or x2, depending on how many you have to do. For secant and cosecant, there's 2 asymptotes, you got to do it twice. And then, to write all the answers, put plus period times n. And if you're not sure, well, how do I find the period? I just gave you a formula for that, right there. That's how you find the period. And you have a formula for each function now, all 6 of them, to find the period. In calculus, it's definitely handy to remember these asymptotes, like to just know, oh, tangent, the first asymptote is pi over 2. Cotangent, 0. For now, if you want to make a chart and reference it, that's fine. Okay, any questions on the table? All right, so now we'll get into finding domain, range, period, asymptotes, amplitude. Why wouldn't I ask you about amplitude with these functions? I'd ask you about amplitude with sine and cosine, but not with the ones we're doing today.
Because they go on the y-axis infinitely.
Yeah, they go up and down forever, so the amplitude is infinite. So the amplitude doesn't really apply here. Okay, but everything else does. Domain, range, period, vertical asymptotes. And now the first one, that's just the basic one. I'm not even doing anything to it. And you know what? I'm not going to find them in that order. Let's find the vertical asymptotes first. So let's go back to the chart. Secant. Those are my vertical asymptotes. Pi over 2 and 3 pi over 2. Now, it says to set each one of those equal to the argument and solve, but look at the argument. There's nothing happening. It's just the basic one. So the asymptotes aren't shifting at all. So asymptotes here are just what you see in the original. Pi over 2 and 3 pi over 2. And what would you put on the end of each one of them to indicate all asymptotes? Yeah.
Plus period times n.
And what's the period for secant?
1. Or, pi, right?
Not pi. Pi is for tangent and cotangent.
2.
2 pi. So plus 2 pi n. So technically that's one way to describe the vertical asymptotes. Now let's write out some of them. And I wanted you to see something. So I'm just going to make a list. We'll call this the first one and the second one. Let's write out some of the first asymptotes. Pi over 2. And then the next one is, where is the next asymptote? The next first asymptote. Yep. 5 pi over 2. Where would the next one be after that? Because now we've established the gap, and that gap would continue. Megan?
9 pi over 2.
9 pi over 2. And the next one, 13 pi over 2. Now, let's write out some of the second asymptotes and watch what happens. So the first one was 3 pi over 2. And the next one, you're going to add 2 pi. So where is the next asymptote for the next second asymptote?
7 pi over 2.
7 pi over 2. How about the one after that? Caleb?
11 pi over 2.
11 pi over 2. And then right after that, 15 pi over 2. So there's really a shorter way to describe all the asymptotes. You don't have to describe them using two separate equations. The asymptotes occur at pi over 2, 3 pi over 2, 5 pi, 7 pi, 9 pi, 11 pi, 13 pi, 15 pi. They occur at all odd multiples of pi over 2. That's a shorter way to describe it. Okay? So for vertical asymptotes, you could say, or all odd multiples of pi over 2. That's a fancier way to describe it because now you've kind of condensed the idea of having two separate equations for asymptotes, and you've taken those two ideas and compressed it into one thought. Makes it easier for someone to look at. Okay. On a test, I'm not super picky if you do that. If you leave what's in the box, that's okay. If you can write all odd multiples of pi over 2, that's even better. Okay, but that requires a little more thought and kind of looking for a pattern in what you see. But there's always a pattern. All right, so we've got our vertical asymptotes. Now, do these kind of functions have breaks in them? The secant, the cosecant. Do they have spots where you have to pick up your pencil? Yeah. So the domain is not all real numbers. What values are you not allowed to use in the domain, in general? Leo?
All odd multiples of pi over 2.
Yeah. So the domain, that's exactly how we're going to say it, is all numbers except odd multiples of pi over 2. All the ones that are not the asymptotes. So all numbers that are not odd multiples of pi over 2. So once you find your vertical asymptotes, then the domain is kind of automatic. Period. I actually already asked that question earlier. You just didn't write the answer. So period is 2 pi. And now the range, well, we already have the graph on the other page. The range here is from negative infinity up to what value in the low part? Yep. Negative 1. So the range is negative infinity up to and including negative 1. Or then where does it pick up again from there? Megan? Yep, 1 to infinity. Yep. So we go from 1 up to infinity. So let's go 1 to infinity. Including or not including? Including. Yep. So there'll be a problem on the test just like that. Okay? I'm going to give you a function and ask you for all that stuff. And I'll be very impressed if you can write it that way. It's always nice. Any questions on describing secant? Okay. Anyone think we need to go through, because I have ones that are a little bit more advanced, but anyone want to go through another basic one that's just the original without any transformation? Okay, so that'd be a good one to practice on your own, but let's do this one. And then we'll finish up with solving equations, which is just like what you did yesterday, okay, finding intercepts. I said period and asymptotes. Let's do it all. Domain, range, period, asymptotes. the last one. Okay, I wrote asymptotes. Obviously, I'm implying vertical. There are no horizontal asymptotes. Right. We can do them in any order we want. Can somebody give me something that they think they know the answer just by looking at it? It doesn't really require too much thought. Yep.
Period.
Yep.
Would be 2 pi over 3.
Yeah, that's good to find because everything else is based off that. Your asymptotes are based off the period. Your domain is based off the asymptotes. So find the period first. Range is kind of its own thing. You could worry about that later. But what's the 3 doing to the cosecant? What kind of transformation? Yep, Sam? I like the idea of the axis you're on. It's definitely an x-axis transformation, but not a phase shift because it's multiplication. Phase shift would have to be addition or subtraction. That's a period change. So we're stretching and compressing along the x-axis. Does stretching and compressing on the x-axis do anything vertical? No. So the range of this function is exactly the same as the range of the original. Negative infinity to negative 1, 1 to infinity. It doesn't matter if you squeeze those U-shapes, tighter together like that. They're still going to have the same y values. All right, so range, negative infinity to negative 1, 1 to infinity. If you're not sure, just graph it and you'll see. Okay, vertical asymptotes. All right. So before I can find where the new asymptotes are going to be, what do I have to know? Yeah?
Where the originals were.
Where the originals were. So for cosecant, before I pull up the chart, how many asymptotes am I expecting per period? 1 or 2? Grace? 2. So let's go to cosecant, 0 and pi. All right, now I'm going to take each of those asymptotes, and what am I going to set them equal to?
You have to do 0 plus 2 pi over 3 times n.
Not yet, because these asymptotes are not necessarily going to be part of this function. They're part of the original, but this is not the original anymore. So what do I have to set each of those equal to? Yeah? The argument. Set them each equal to 3x. Now, because one of them is 0, obviously that one won't change, but the other one will. So now we have asymptotes at 0, and I'll do what you mentioned in a second. And I have another asymptote at pi over 3. So those asymptotes are going to repeat every period. Let's go back up. Our period is 2 pi over 3. So really, do we need this 0 plus? No. If you're going to add 0, you don't even really need it. So that's the equation for where your first asymptote occurs. That's the equation for where the second one occurs. Let's see if we can combine those two into one thought. So your first asymptote, 2 pi over 3. The next one is going to be 2 pi over 3 later. So that's 4 pi over 3. Next one, 6 pi over 3. Eventually, when you get a little quicker at it, you don't even need to make this list to look at the pattern. You can just kind of figure it out. So those are the numbers from the first asymptote. Second asymptote, pi over 3. The next one is going to be add 2 pi over 3 to that. What do you get if you add 2 pi over 3 to pi over 3? Yeah? You get pi. I'm going to write it as 3 pi over 3 for a second just to see the the pattern. Now the next one is another 2 pi over 3. And another 2 pi over 3. So could anyone describe where my asymptotes occur here? Yeah?
Every value of pi over 3. Like every multiple.
Every multiple of pi over 3. Perfect. Yep. So the vertical asymptotes are all, not odd or even this time, all multiples of pi over 3. So then lastly, what would my domain be? Yeah? All real numbers except the multiples of pi over 3. Yep. So all reals except the ones that are multiples of pi over 3. Okay. And now the last thing, it just wanted us to graph it on the screen and show 2 periods. Well, I need a screen width of 4 pi over 3. I'm sure everybody can do that part. The part I want to show you is the parentheses to type it in. Cosecant is 1 over what function? Yeah. 1 over sine. So to type it in, you have to type 1 over sine 3x. Now, if there was an amplitude change in there somewhere, then you would also need this. In that problem, it's unnecessary. But now you could squeeze a number in front between the parenthesis and the sign if you had to. If you don't put parentheses in, it won't work. For this one, it would. All right, so now window, I'm going to go 0, and 2 cycles would be 4 pi over 3. 4 pi over 3. And that looks good. The way we did it, we didn't cut anything off. It's exactly 2 cycles, very, very nicely laid out. Okay, any questions on that? All right, so it's a little bit at first to try to get used to it, but once you do get used to it, it is a fairly mechanical kind of thing. You got a table, you look things up, you kind of do the same thing every time. Never changes. All right, so last thing we'll look at is solving equations on the calculator. Okay. Keep in mind that if there's one solution, there's infinite solutions. Okay, because trig functions are periodic. At least if you're graphing like a trig function and a line. There is a way you could have a trig function and another graph and not get infinite solutions if you did something like this. If I said to you, where do those graphs intersect? They're not going to intersect forever. The trig function's going to go on forever. But the parabola doesn't go left and right forever in the region that the trig function does. It starts going left and right forever above it. Right? So if you graph a line and a trig function, you're good, infinite solutions. A trig function and a trig function, yep, usually infinite solutions, if they cross at least once. Right, so the next part, I'm going to skip it because we've already done it. You find one solution, and then you put plus the period times n. It's just like finding asymptotes. Find one, then represent all. And remember, n is an integer. Okay, let's try this one. So find all solutions to cosecant x equals negative 1.6. Okay, so it said all. So, what would I type into y1? tell me how, please, how to type it. Yep.
1 over sine.
Perfect.
X.
1 over sine x. How about y2? Yep.
Negative 1.6.
-1.6. And now, when I'm finding the solutions, I don't want to focus on more than one cycle. It says, wherever I had it, find all the solutions in one period. What's the period of cosecant? Yep, 2 pi. So on your window, don't confuse yourself. Focus on one cycle. Don't look at anything more than that. And how many solutions do I get per period here?
2.
I get 2. So I'm going to find those 2 solutions, and then I'm going to represent that they keep reoccurring regularly. So second calc intersect. Okay, so the first one is 3.817. And the second one, does anybody already have the second one?
5.608.
5.608, thank you. And how often are those 2 answers going to keep reoccurring? Okay? Infinitely. And what's the frequency of the infinite amount of answers? How often?
Plus 2 pi n.
Plus 2 pi n. Yep. So if you wanted to know where's the next time that you're going to get an answer, take 3.817 and add 6.28, to get a rough answer. It's plus 2 pi n. It'd be kind of hard to combine those 2 solutions into one solution, like we did with asymptotes. If you think about it more, maybe you could see why that would be harder to do. So you really have to write each answer separate. Depending on the answers, if they lined up nicely, you might be able to combine 2 separate solutions into one thought. But for now, don't worry about that. All right. Let's go like this. Okay, so let's find all solutions where tangent x equals 2.5. Now, if you visualize in your head the graph of tangent and a horizontal line, how many solutions should we expect per period here? Yep, just 1. Remember, tangent looks like this, horizontal line looks like that. Find that intersection point. Tangent, a little easier to type in because you have a button for it. So just type tangent, 2.5. Now I only want to focus on one cycle. Okay, so for tangent, I'm going to focus on 0 to pi. That's fine. It broke the period in half, but that doesn't matter. Okay, it doesn't matter what solution you find. You could find this solution. You could find the one in the next period. You could find the one in the previous period. As long as you find one solution and put plus the period times n, that covers all of them, no matter which one you start with. Okay, so the first positive solution is 1.190. And Shauna, what am I going to put on the end of that to represent all?
2 plus 2.
If you put plus 2 pi n on this one, we would lose half of our solutions because the solutions occur more frequently than 2 pi. Pi n, yeah, because the period is pi. Any questions on that? All right, so just a couple reminders about the take-home. Okay, So homework is the take-home test. Tomorrow's a half day, and I see you guys period 2, first period tomorrow. So the test is due at 7:45 a.m. on 12/22. Late tests, all 0. So if you're going to be late or you think you're not going to be here or something's going to happen, then take a picture of it and send it to me. Or email, just something like that. Okay, any concerns or questions about that? Because if that is a problem, you could always take it anytime during the day today. The test is ready, or after school today if you needed to.